shape of the container, okay, in the sense that in our case the container is formed by magnetic fields or optical fields, so it can be compressed in along one direction more than the other direction. So the shape of the cloud of atoms can be like an ellipsoid in the trap. Now, if your atoms are in a thermal state, once the trap is turned off, these atoms are going to come out of the trap and fall, and they are also going to expand. If it is a thermal cloud of atoms, they expand isotropically. So circular, there is a circular, it's basically a spherical cloud of expansion of atoms. But if it is a Bose condensate, it's like a single macroscopic wave function it's a quantum state inside this trap. Now, if there is an ellipsoidal collection of this quantum state, the macroscopic state of these atoms, what happens is that when you switch off the trap, since the extent of the spatial extent of this wave function has to follow Heisenberg uncertainty relationship, along the direction where the spatial extent is less, the momentum uncertainty is more. Along the direction where the spatial extent is more, the momentum uncertainty is smaller. So once you turn off the trap, the asymmetry of the cloud changes as it is falling down. Along the direction where it is smaller, it becomes longer. Along the direction where it is larger, it expands lesser. So the asymmetry of the cloud changes. So that is a signature of saying that whether your cloud has undergone a phase transition to Bose condensation or not. So this is what we use. So here is what you see here. There is a almost symmetric expansion, and here there is an asymmetric expansion of the cloud once we turn off the trap. I will show you how we make the Bose condensate. So this is just again a revisiting how we achieve a Bose condensate. So you have the particles, and then you have their associated fuzziness with them, along with them, and these wave extent does not overlap with each other. But as you cool them down and increase the density, then all these the wavy nature of all these particles, they start interfering with each other and creates a giant single matter wave kind of a wave. And that's where you get a macroscopic occupation of the ground state in this confining potential. Now, in our systems, in systems where we create Bose condensate in the lab, there are various stages that one goes through. Now, this is the stage where it uses 3 sets of lasers from all the 3 directions, 6 directions, orthogonal directions, counter-propagating, to actually impart the momentum of photons onto the atoms to cool these atoms and confine them. At this stage, the phase space density is about 10 to the power minus 6 or so. Temperatures around several hundred microkelvins, atoms about a billion of them. Then we transfer them either in a magnetic trap, different types of magnetic trap, or through an optical trap where we use focused laser beams, intersecting focused laser beams, which create an optical potential where you confine these atoms. And then once you confine them in this potential, there is a fraction of hot atoms, fraction of cold atoms. The distribution, velocity distribution, is basically governed by the Maxwell-Boltzmann distribution. Then what you do is that you cut the tail of the Maxwell-Boltzmann distribution, throw away the hotter atoms, and let the remaining atoms, you throw away the hot atoms by cutting the confining potential. Remaining ones rethermalize by collisions, and they become colder and denser, and then at some point you go through the phase transition. So this is an animation of the actual system. I'll just turn it on. So at this end there is this is a vacuum system. This is almost like the real system that we have in the lab. So there is a metal of rubidium here which is heated to about 80 degrees, and then there is a beam of atoms that's generated. And the stream of atoms initially is at about 400 meters per second. The atomic velocity is about 400 meters per second here, which is very fast. We cannot capture them in the 6 laser beams. So there is a counter-propagating laser beam which slows these atoms down from several hundred meters per second down to 20 meters per second approximately. And there is some kind of a magnetic field profile across the axis, which is designed to keep all the atoms as their velocity is slowing down because of the scattering of photons from the counter-propagating laser beam. As they slow down, they go out of resonance from the light because of Doppler shift. But we have to keep them continuously decelerating. So the magnetic field along the axis brings the atomic levels always closer to the photon's wavelength frequency, and they always continuously get decelerated by the time they go to towards the end of this tube, which is called as a Zeeman slower. This technique of Zeeman slowing was an important step in laser cooling techniques, which was developed by William Phillips in what's that in the US, the university name where he comes from. He was also it was developed in NIST actually, but he was associated with the Maryland University. So that's where this technique was developed. So this is one of the most important contributions from Bill Phillips, which won him the Nobel Prize, the development of this Zeeman slowing technique. It's called the Zeeman slower. The reason that it is important is that in the next step, where we are going to actually cool these atoms, so there are these 6 laser beams which are used to collect this stream of atoms which is coming from there close to 20 meters per second. You get a blob of about 1 billion atoms at several hundred microkelvin temperature. And then what we do is that we transfer them into turn off the light and transfer them into a magnetic bottle which is created by the magnetic fields of these 3 different coils here. The light is switched off and the atoms are magnetically trapped, and it becomes an ellipsoidal cloud in the magnetic bottle. Now the atoms are very hot in the sense the phase space density is low. Although they are few hundred microkelvins temperature, the phase space density is low. So we have to do forced evaporative cooling. So what we do is that the hotter atoms which are at the outside, we throw them away by flipping their spins. They are all spin polarized. We shine radio frequency, we blow RF onto these and throw away the atoms on the periphery. So as a function of time, the remaining atoms, they rethermalize to lower and lower temperatures and becomes denser and denser. And after that, after a certain point, you get a Bose. One second. So after a point, you get these atoms into the Bose condensate. So as I mentioned earlier, the ellipsoid was horizontal. Once it is a Bose condensate, as it is dropping down, the asymmetry changes direction. As I show you here, it becomes like that, vertically elongated because of the uncertainty relationship. And the way we do diagnosis is, we shine a pulse of light and take an image of the density of atoms and then look at the image. Now all the physics experiments that one has to do, they are done as soon as the Bose condensate is formed. We do the whatever physics experiments need to be done, matter wave interferometry or quantum simulations or whatever. Take the image like this and do your analysis for whatever is happening. So I'll quickly give you an example of one such example of using matter waves for atom interferometry. So there are many experiments that can be done, as I mentioned. You can do quantum simulations, you can study many body physics, the physics of Anderson localization, you can build very precise atomic clocks, and you can do matter wave interferometry. I'll give you a quick example of matter wave interferometry that we have been doing in the lab, and That matter wave interferometer is basically similar to, you can imagine the simplest form of a matter wave interferometer is similar to a Mach-Zehnder interferometer of light. So you can imagine that here you have a light beam which is going through a beam splitter through two different paths, and then there are mirrors on these sides which reflect them back, and then there is a final beam splitter which is going to merge the wave packets. Now in an atom interferometer, instead of light, you use a packet of an atomic wave packet, and then instead of beam splitters and mirrors, you use light pulses which are formed by standing waves to split this wave packets into different momentum states. So the wave packets actually are split into different momentum states, and then you interfere them and look at the population of atoms across the two ports of the interferometer, and whatever phase shift is picked up along the two directions, the interference pattern or the population of atoms changes at the output of the wave. Now why atoms? For example, one example is a Sagnac interferometer, where you have a Mach-Zehnder interferometer on a rotating table. Now the phase shift that is picked up on such an interferometer at the detector here is proportional to the rate of rotation and the area that is covered. So one can use a rotating Mach-Zehnder interferometer to build a gyroscope to detect rotation, to make rotation sensors. In fact, people use laser gyros to build this. Now, if you look at the rest mass energy of atoms and photons, the ratio is of order 10 to the power 11. So, for the same area, you can gain theoretically by so many orders of magnitude if you use atoms. So, atom interferometers are becoming very, very popular for making very sensitive interferometers. Although the area can be much smaller with atoms, you can compensate that, but at least get to about 10,000 times or a million times better than a matter wave, a light interferometer. Now, another important thing with atoms is that you can make them sensitive to many things like magnetic fields, electric fields, or gravitational fields, because they are massive. They can have magnetic dipole moment, they can have electric quadrupole movements, etc. And depending on the choice of atom, you can make them sensitive to any of these and build very sensitive interferometers. One example is building a gravimeter to detect local gravitational acceleration. Now, you know that we all know G is about 9.8 meters per second square. But if you start measuring it more and more precisely, it starts becoming sensitive to a lot of things: latitudes, longitudes, altitude, density of the soil underneath, rocks, etc. What is whether the moon is going above you or not? All these factors make it make this value change in different decimal places, and it is very important for strategic applications also to detect underground tunnels, for example, without the use of any electromagnetic radiation. So they are very sensitive. Now the advantage with atoms is that atoms are absolute gravimeter, absolute sensors. They don't need calibration, as opposed to some other sensors like suspended masses and all that. They need regular calibration. They are not absolute sensors. And they are used for many, many things, like in civil engineering for detection of mine shafts, sinkholes, to detect water tables underneath, to map whether the large plates are moving across under the ground, to do gravity mapping, for rotation sensing in general, and you can also use them for GPS-free navigation, because if you are in a location or environment where GPS signals are denied, then you don't have anything to navigate. All you can do is if you have a system